In order to understand the section on rates of reactions, it is first necessary to understand collision theory. Now, collision theory explains to us how reactions happen. So, it is based on the principles that we learnt in grade 9, where we said that all matter is made up of particles. Those particles are in constant motion. We obviously remember that the particles of a gas are moving faster and greater distances than those of a solid and those of a liquid. As a result of that constant motion, these particles are constantly colliding with each other. But now, in order for a reaction to take place, we need very specific conditions to be satisfied. So in most reactions, most of the collisions we say are unsuccessful, meaning they do not lead to a reaction. What collision theory tells us is it tells us that there are 3 requirements in order for a successful collision to occur, which means that a chemical reaction can happen. So if we look at a hypothetical reaction between hydrogen, which we know is a diatomic element, so it comes in the form H2, and iodine, which is also a diatomic element in the form I2. We need these 2 molecules to collide with each other and hopefully end up by forming hydrogen iodide molecules. So the first principle of collision theory says that a successful collision requires these molecules to collide with each other, which means that they must bump into each other so that there can be a transfer of electrons and a bond that can form. So that is the first condition or requirement, that they must collide. Now, as we can see here, if these 2 molecules are to collide in this orientation, what that would then mean is that we are trying to form a bond between this hydrogen and this iodine without providing an alternative for this hydrogen and this iodine, because they are not in contact. So when we say the correct orientation, what we are saying is that they must collide with each other in such a way so that every atom present is able to form a new bond. So that is what we mean with correct orientation. This over here would be an incorrect orientation. This over here is a correct orientation. This, just for interest's sake, is called the activated complex. And then finally, the other requirement is that because we know that all elements have electron clouds around them, we know that in order for a collision to occur, the atoms need to have enough energy to approach each other and overcome that electron cloud repulsion. We know that the electrons of each atom are both negatively charged, so they would try to repel each other. So it is necessary for elements and atoms and molecules to have enough energy to overcome that force of attraction so that those electrons can pass each other, and these electrons can form a bond with that nucleus which contains the protons, and these electrons can form a bond with that nucleus. So in order for a successful collision to occur, firstly the molecules must collide. Secondly, they must collide in the correct orientation so that a bond is capable of forming for all atoms. And finally, they must collide with enough energy to overcome what's called the electrostatic force of repulsion between each atom's electron cloud. The rate of reaction in chemistry is incredibly important because some reactions can take very long periods of time, for example, substances that rust. Other reactions can be incredibly quick and powerful, and explosions are common examples of those types of reactions. So when we define the rate of a reaction, the first thing is we need to understand some notation. When something is drawn in square brackets, it refers to the concentration of that substance. So this over here would be read as the concentration of hydrogen. So we define the rate of a reaction as the rate at which the concentration of either our reactants or the products changes. We can define it by either reactants or products because we know that the conversion between them is governed by a fixed ratio, so the rate of change for both will be equal. Now we know from collision theory that in order for a reaction to take place, the particles must collide with each other, and all particles are constantly colliding, and only a small fraction of those are actually effective collisions. So most of the changes that we can make to a chemical reaction change the number of total collisions, which as a result increases the number of effective collisions. The first change that we can make, or the first factor that affects the rate of a reaction, is the nature of reactants. That basically just means the phase that those reactants are in. We remember from the particle model of matter that the phase can either be solid, liquid, or gas. We know that there are other phases, but these are the ones we will be dealing with. We also know that particles in gases move much faster than those in liquids and also those in solids. Since they move faster, they have more collisions. More collisions means more effective collisions. So we say that gases react faster than liquids, which react faster than solids. When we're talking about surface area, what we are saying is that if you have a square of substance that is trying to react, the reaction can only take place on the surface. The reaction cannot take part with one of the molecules in the middle because it is not in contact. So when we increase the surface area, if you continually cut the substance down into smaller and smaller pieces, you're increasing the surface area where reactions can happen, thereby increasing the number of collisions, thereby increasing the number of effective collisions. So what we'll often say is, when we say we increase the surface area, we are increasing the amount of contact surface area. So therefore you will find that when we have a substance that is in powder form, meaning it is very, very small pieces, it has an incredibly big surface area, therefore there's space for more collisions and more effective collisions. Increasing the concentration and increasing the pressure of a substance are both very similar in that they are increasing the number of particles per unit area. So if you only have 4 particles in a certain area and they are bouncing around, they will eventually collide with each other, but the number of collisions will be low and therefore the number of effective collisions will be even lower. Whereas if you increase the number of particles, either by increasing the concentration or by increasing the pressure, pushing them closer together, you will increase the number of collisions and therefore the number of effective collisions. A temperature increase increases the speed at which particles move around in a container. Since they move around faster, they would therefore collide with each other more often. Since they collide more often, there would be more effective collisions. And finally, the catalyst provides an easier path for the reaction to happen, and this one just increases the number of effective collisions without necessarily changing the number of collisions. So when we talk about factors that affect the rate of a reaction, they are all essentially doing the same thing except for the catalyst. These 5 are increasing the number of collisions. By increasing the number of collisions, they will increase the number of effective collisions. The catalyst, on the other hand, actually increases the rate of effective collisions. We know that chemical reactions happen because atoms want to form bonds that make them more stable, and as a result of that stability, we can say that they have a certain amount of potential energy. So in a typical reaction, we would start out with our reactants, in this case that is hydrogen and iodine, and as a result of their stability, or the stability of those bonds, they have a certain potential energy. And we can write here that that is hydrogen and iodine's combined potential energy. We know that the hydrogen molecule is just 2 hydrogens that are combined, and the iodine molecule is 2 iodine atoms that are combined. We also know from collision theory that in order for a reaction to happen, a certain amount of energy is required in order for the reaction to be successful, or in order for the collision to be successful. So when that energy is supplied, you can see that the potential energy would increase. We say that that amount of energy that is supplied, the amount of energy from the energy of the reactants to the maximum amount of energy, is known as the activation energy, which is the energy required for a reaction to start. For interest's sake, as explained in collision theory, in order for this to happen, it forms what is called the activated complex, which is a transition state where the collision has occurred, it's occurred in the correct orientation, and we have formed a transition state. We have formed something that has the ability to go back to forming hydrogen and iodine, but it also has the ability to break apart into two new molecules, those of hydrogen iodide. Now, in an exothermic reaction, which is what we have here, when that happens, the amount of energy or the potential energy that hydrogen iodide molecules have is lower, meaning it is a more stable molecule than individual hydrogen and iodine molecules. So what we say is that the products in this reaction, the product being hydrogen iodide, has a lower potential energy than the reactants. And as we can see here, there's a certain amount of energy that has been given off in this reaction because these compounds started with a certain potential energy and they ended with a lower potential energy. And we call that the enthalpy change. It is basically the amount of heat that is given off in a reaction. As we can see in this reaction, the enthalpy change has been negative, meaning it has given off energy, and we would write that as either delta H is less than 0, or if you know for the specific reaction, this one, for example, has an enthalpy change of negative 9.48 kilojoules per mole that reacts. Both of these are just ways of saying that the products are more stable and therefore have a lower potential energy than the reactants, which means that this reaction, every time hydrogen and iodine combine to form hydrogen iodide, every time that happens, a certain amount of energy is given off. We say that energy goes into the system, and the system heats up. So exothermic reactions are defined by a negative enthalpy change, as well as a reaction mixture, the entire mixture of this reaction that heats up over time. We know that all reactants will have a certain amount of energy as a result of the bonds that they have formed. So in this example that we have here, our reactants are nitrogen and oxygen, and they have a certain energy as a result of their bonds. We also know that in order for a reaction to happen by collision theory, those two particles must collide with each other. We know that we have our two nitrogen atoms that form a molecule and our two oxygen atoms that form a molecule. We know that in order for them to react with each other, they must collide with each other. They must also collide in the correct orientation that allows the possibility of new bonds to form. We know that there's a certain amount of energy that is required in order for that to take place. We know that that amount of energy is known as the activation energy, the amount of energy required for a reaction to start. Now, in an endothermic reaction, we will find that the products that are formed have a higher potential energy than the reactant. So the product here, nitrogen monoxide, as we can see, has a higher potential energy than our reactants. What this means is that there is now energy that needs to be absorbed in order for us to go from our reactants to the products. A certain amount of energy is required. We call that the enthalpy. Once again, the enthalpy is the heat of the reaction. And what this is telling us is that in every reaction that happens, a certain amount of heat is taken in order to form nitrogen monoxide. So we say that the enthalpy change is positive. In this case, the enthalpy change is 180.5 kilojoules per mole. And what that means is that this reaction is constantly absorbing energy from the environment, which means that the environment cools down. So we say endothermic reactions are defined by a positive enthalpy and a cooling down of the reaction mixture. What we can also see here is that we can demonstrate the effect of a catalyst on this reaction. So we know that a catalyst is one of the few changes to a reaction that changes the rate without changing the number of total collisions. What the catalyst does is it provides an alternate path in order for this reaction to happen. So as we can see, the activation energy for the catalyst, we say the catalyzed activation energy is less than the original activation energy, meaning that less energy is required for this reaction to happen, which makes the reaction happen easier or faster or more successfully. What we can also introduce here is the concept of a reversible reaction. What this says to us is that although the forward reaction here, where nitrogen reacts with oxygen to form nitrogen monoxide, is endothermic, the reverse reaction in which nitrogen monoxide breaks apart to form nitrogen and oxygen again would obviously then be exothermic, because we are then reading the graph from the other side. So for any reversible reaction, if the forward reaction is endothermic, the reverse reaction would be exothermic, and vice versa. Temperature is a measure of the average kinetic energy of the particles in a system. That is shown on the Maxwell-Boltzmann distribution curve, because when we say that a system has a certain temperature, say T1, what this curve tells us is that the particles' energies are distributed across the entire spectrum, meaning that particles range in energy from 0 to a theoretically infinite value, in much the same way as when the average for a class test is 60%. That does not mean that every single person in the class got 60%. It means that the marks ranged from 0 to the maximum for that test, with the average being 60. So what this curve shows us is that a particle can have a very, very small value of energy, but it can also theoretically have a very, very large value for its kinetic energy, but the average energy is centered around T1. Now, the reason why this is important is because in rates of reaction, we say that there's a certain activation energy that is required in order for a reaction to take place. Now, the way we would read this graph is by looking at it and seeing that only the particles that have more energy than that required activation energy are able to take part in that reaction, which in this case is a very small fraction. Now, there are two ways in which we can increase the number of particles that have that required activation energy. The first way is to increase the average temperature. We do that by heating the system, which would mean that we would create a new curve that is centered around a higher value. What you should see here is that the average temperature, T2, is now greater than T1. And you should also see that the maximum number of particles has decreased slightly because the curve has been shifted to the right. What this does mean now is that since the activation energy required for this reaction has not changed, it means that there's a far larger fraction of molecules that is now able to take part in this reaction. The second way in which we can increase the number of particles that can take part is by using a catalyst. We know that a catalyst lowers the required activation energy. It does that by providing a different path, and what that then does is it opens up the path for more molecules to take part in that reaction. We know from collision theory that there are various physical factors that can affect the rate of a reaction. We can demonstrate this with the reaction between zinc and hydrochloric acid by making a number of changes and observing the rate at which that reaction proceeds. So the first thing that we do is, because we know that hydrogen gas is produced, we add some detergent that will form bubbles or foam as the reaction proceeds, and obviously form more foam if more hydrogen gas is produced. In our first test tube, we have zinc granules, also known as zinc chunks, with 1 molar hydrochloric acid. The second test tube, zinc granules with 4 molar hydrochloric acid. The third test tube, zinc granules with 1 molar hydrochloric acid with a copper catalyst. The fourth test tube, zinc powder with a 1 molar hydrochloric acid solution. And the fifth test tube, zinc granules and 1 molar hydrochloric acid, but placed in a hot water bath to speed up the rate of reaction there. So what we're going to do now is we're going to add the hydrochloric acid to each of these test tubes and observe the rate of each of these reactions and how they proceed. Now, what we would expect to see is that our first reaction here, zinc granules with 1 molar hydrochloric acid, we expect this to be our control reaction. As you can see, there are granules in all but one of the reactions, and there's 1 molar hydrochloric acid in all but one of these reactions. So this should be our control, and we can monitor how much foam is formed in this reaction. What we then have in our second test tube, this one over here, is we have a 4 molar solution of hydrochloric acid. Once again, by collision theory, because there are now more hydrochloric acid molecules present, we would expect more collisions and therefore more successful collisions to occur and a faster rate of reaction, and we can start to see that happening here with far more foam forming in the second test tube than in our first test tube. In our third test tube, we have zinc granules and 1 molar hydrochloric acid. The one difference here being that we now have copper that acts as a catalyst. We know that a catalyst provides an alternate path for the reaction to proceed by, and so we would expect this reaction to happen faster than our reaction in test tube number 1, and we can see that that is indeed the case. We can see that more foam is formed, meaning that more hydrogen gas is being formed in that test tube. The fourth test tube is a more complicated one. This is now zinc powder. So instead of using zinc granules or zinc chunks, we have now ground it into a powder, which means that we have increased the surface area of the zinc. So by collision theory, that tells us that the reaction should proceed at a faster rate because there are more opportunities for collisions and therefore more successful collisions. Although what we often find experimentally in this reaction is that the zinc oxidizes, which means that the zinc does not react as readily with the hydrochloric acid. So this is one where theoretically and experimentally we might find different results. And the final reaction that we have here is once again zinc granules and 1 molar hydrochloric acid. The big difference here being that it's occurring at a much higher temperature, which explains to us why that reaction would proceed far faster, because we know that as you increase the temperature, you increase the number of molecules that have the required energy in order to form a successful collision, and thereby we would increase the rate of the reaction. So here we have a good layout of an experiment that allows us to compare the rates and the rate changes by different factors. Because we have used a constant in each experiment, we have either kept the surface area constant by using granules, or we have kept the concentration constant and only made one change to each test tube. This allows us to easily tell the difference between why this reaction is slower than this one, because the only change is a concentration change. And we can compare this reaction to this reaction because the only difference here is a catalyst. In the same way, that is why it's so important to have a control test tube which allows you to make individual changes for comparison's sake. We're doing a demonstration of rates of reaction to show how concentration changes affect the rate at which a reaction happens. So here we have a precipitation reaction occurring between sodium thiosulfate and hydrochloric acid. That forms a number of products, but one of them is a solid that forms a white powder that forms a precipitate that drops to the bottom of the petri dish, and as a result we'll see the X's marked on these petri dishes disappearing, and what we've got is different dilutions of our sodium thiosulfate. The concentration and quantity of hydrochloric acid remains constant, and so we're going to see what effect changing the concentration or the dilution of sodium thiosulfate has on the rate at which this reaction proceeds. So we're going to start by adding our sodium thiosulfate into each petri dish. You'll see that solution A is 75 moles sodium thiosulfate and 25 moles water. Solution B is 50-50, and solution C has a 25 moles sodium thiosulfate and 75 moles of water. What we're now going to do is we're going to simultaneously add 4 milliliters of 1 molar solution of hydrochloric acid to each of these, and we are going to observe the rate at which each of these reactions happen. It's important to add the acids all at the same time to ensure that the reaction proceeds at the same rate. Now, what we would expect to happen here is that as a result of collision theory, which says that in order for a reaction to occur successfully, there must be more collisions, and more collisions would result in more successful collisions, we would expect that the higher concentration of sodium thiosulfate will result in more solution or more particles present, therefore more collisions between sodium thiosulfate and hydrochloric acid. So we would expect the precipitate, that white powder, to form faster, which is what we see happening here. The white powder obviously drops to the bottom of the petri dish. As it drops to the bottom of the petri dish, it forms a layer that stops us from seeing that X that we have marked at the bottom. You obviously can't experience this, but there's also some gas that is being released that we can smell, and then our water and sodium chloride that are being formed here. And as expected, the higher concentration of sodium thiosulfate has resulted in more collisions, meaning more collisions per second, meaning more successful collisions, which results in a faster rate of reaction, which is why we can see the precipitate has formed far faster in this reaction than in the next one, where we have a 50-50 dilution ratio, where we can see the reaction has also proceeded faster to form more precipitate than our final reaction, in which we are still waiting for enough precipitate to form to cover that X that we have marked on the petri dish. So once again, we know from our reaction rates that there are a number of factors that do influence the rate of reaction. In this reaction, though, by ensuring that these reactions all start at the same time, the room temperature and the temperature of these solutions is the same for all of them, means that the only factor that we have changed in this reaction is a concentration, and we can clearly see that a higher concentration leads to more collisions, which results in more successful collisions, which eventually results in a faster rate of reaction. And we can slowly see the precipitate here forming that will eventually cover the bottom of that petri dish. And we can now see that we're nearing the end of the reaction, where that X marked at the bottom of the least diluted sodium thiosulfate solution has all but disappeared, and once again showing us that the higher the concentration of reactants in a reaction, the greater the speed or rate of that reaction will be.